Picture yourself sitting in window seat 14A. You're cruising at 30,000 feet, and you can feel that slight rumble of the jet engines under your feet.
Oh, yeah, the best feeling. Or, maybe you are just on your couch, controller in hand, navigating some completely digital, hyper-realistic video game world.
Right, exactly. Two totally different environments. But in both of those scenarios, your physical safety in the air or your digital immersion on the couch relies entirely on, well, a teenager in India cramming for a math test.
Which, I mean, it sounds like an exaggeration when you say it like that, but that is the beauty of our source material today. We are looking at an incredibly detailed set of study notes for CBSE Class 12 Mathematics in India.
Specifically Chapter 10, right? Sections 10.4 to 10.6.
Exactly. The header just simply reads, Day 28, Vector Operations and Engineering Applications.
So welcome to today's deep dive into the source material. We are so thrilled to have you sitting at the table with us. And our goal here, just to be clear, is not to put you through a grueling high school math lecture.
No pop quizzes today.
Yeah, no quizzes. Instead, we are going to extract the most important nuggets from this document to uncover a secret that's basically hidden in plain sight.
Yeah, a really fascinating one.
We want to show you how abstract pencil and paper concepts, things like vectors, dot products, cross products, are actually the hidden mathematical engines running our entire modern world.
Because mathematics is so often misunderstood. People think it's just a series of arbitrary rules you have to memorize for a test.
Just numbers on a chalkboard.
Right. But it is actually the fundamental language of reality. And what makes these specific study notes so compelling is how directly they map this foundational geometric theory to the absolute cutting edge of aerospace engineering, electromagnetism, and computing.
Everything happening around you right now.
Literally everything happening around you right now is governed by the principles in these pages.
Okay, let's unpack this.
Yeah.
Because before we can, build a massive airplane or render a lush 3D landscape, we really need to understand the building blocks.
We have to start with the basics.
Yeah, so the text starts with the anatomy of a vector. And in its simplest geometric form, a vector is basically just an arrow in space.
Just a simple arrow.
Right. It possesses two crucial pieces of information. It has a length, which the math calls its magnitude, and it has a specific direction.
To visualize this for you, imagine you're just standing in a room, you take 3 steps forward, and then you take 2 steps to your right.
Okay, pretty simple.
That movement can be perfectly represented as a vector. And the notes detail how you combine multiple movements like this through what they call vector addition.
Oh, right. Geometrically, this follows what the notes call the triangle law or the parallelogram law.
Exactly. You are essentially drawing a physical path.
So if you take one path, that's your first vector, and then from the end of that path you take a second vector, the triangle law just draws a straight connecting line from your very first starting point to your final ending point.
It's a shortcut.
Yeah, it elegantly captures your total displacement. And algebraically, the text explains this translates to element-wise addition.
And we should probably clarify what element-wise means in this context, because it is super foundational.
Good idea.
A vector in three-dimensional space is defined by its coordinates on the x, y, and z axis. So essentially, how far it moves left, right, up, down, and forward, backward.
Right.
Those individual coordinates are its elements. So when you add two vectors together element-wise, you aren't doing any complex trigonometry.
No intense angles or anything.
Not at all. You are simply adding the x-coordinate of the first vector to the x-coordinate of the second, the y to the y, and the z to the z.
It is surprisingly intuitive when you break it down into those basic coordinates.
It really is.
But the text then introduces a way to manipulate a single vector, a concept called scalar multiplication.
Right, introducing a scalar.
And a scalar is just a fancy mathematical term for a standard everyday number. It has a size, but absolutely no direction.
Just raw quantity.
Yeah. So the notes explain that when you multiply a vector by a scalar, which they represent by the Greek letter lambda, it scales the vector's magnitude by the absolute value of that lambda.
Think of it as basically stretching or compressing that original arrow. You are changing its length completely without altering the path it is pointing down.
To put this in everyday terms for you listening, imagine setting up a stereo system in your house. Scalar multiplication is basically just the volume knob.
Oh, I like that.
Yeah, if my vector represents a sound wave traveling across the living room from the speaker directly to your ear, turning that volume knob up, say multiplying the wave by a lambda of 2 or 3, that scales the magnitude.
It makes it louder.
Exactly, it makes the physical sound much louder, but the sound wave is still traveling in the exact same direction toward your ear.
That perfectly illustrates the magnitude aspect of it. However, the text adds a critical twist regarding the direction.
Oh, right, the negative numbers.
Yes. It states that if lambda is less than 0, if you are multiplying the vector by a negative number, it entirely reverses the vector's direction.
Just completely flips it.
The arrow flips 180 degrees.
So, continuing with the volume knob analogy, that would be like having a stereo where you could turn the dial below 0.
Which would be terrifying.
Right. If you hit negative numbers, the sound wouldn't just mute. The physical sound waves would actually have to reverse their course in the air.
They pull away.
Yeah, they'd travel backward from your ear and disappear back into the speaker.
While that is obviously impossible for a living room stereo, it is incredibly vital for physical reality. I mean, engineering relies entirely on manipulating the magnitude and direction of real-world forces.
Like holding things up.
Exactly.
Yeah.
Suppose you are designing a massive suspension bridge. You calculate this huge downward force vector from the weight of all the cars on it.
That's a lot of force pointing straight down.
Right. So you need the bridge supports to provide an upward force of the exact same magnitude, but in the exact opposite direction, just to keep the bridge from collapsing.
So multiplying that original downward force by a negative scalar is the mathematical mechanism that makes that structural calculation possible.
It is the math that keeps the bridge standing.
That is wild. Okay, so we now have the ability to scale individual vectors, stretching them out or flipping them entirely around.
Right.
But physical reality is rarely just one force acting in isolation, right? We need to know what happens when two totally different vectors interact with each other.
They had to bump into each other eventually.
Yeah, and the source introduces the dot product, also known as the scalar product, to measure this exact relationship.
And the formula here is, well, it looks a bit dense at first.
Yeah, it's vector A dot vector B, which equals the magnitude of A multiplied by the magnitude of B multiplied by the cosine of theta.
With theta just being the angle between those two intersecting vectors.
Right. And I know the inclusion of the word cosine might bring back some stressful memories of high school trigonometry for you listening, but the text provides a really beautiful physical way to ground this equation.
It does. It states that the dot product measures the parallel projection of one vector onto another.
Which is such a cool concept. Imagine one vector is a long, flat stretch of highway, and your second vector is an airplane taking off from it at a steep angle.
Okay, I could see that.
If the sun was directly overhead, shining straight down, that climbing airplane would cast a shadow onto the highway below it.
Right onto the tarmac.
Exactly. The dot product is essentially measuring the physical length of that shadow multiplied by the highway vector. It basically calculates how much these two completely separate forces align with each other.
It tells us how much they share the exact same physical path.
Yes.
And measuring that shared path leads to an incredibly important concept in the text called the orthogonality check.
Oh, this part blew my mind a little bit.
It's so cool. The source explicitly states that if the dot product equals 0, and neither vector is just a 0 vector itself, then the two vectors are strictly orthogonal.
In simply terms, they are perfectly perpendicular. They meet at exactly a 90-degree angle.
Right. And because the cosine of 90 degrees is exactly 0, the entire mathematical equation just zeroes out entirely.
Yeah. So what does this all mean? If the dot product is 0, does that essentially mean these two forces have absolutely zero influence on each other's path?
What's fascinating here is the sheer geometric beauty of orthogonality. It is precisely as you deduced.
Wow.
You can have two incredibly powerful forces existing in the exact same physical space, intercepting at a specific point, but because they are perfectly perpendicular, they remain mathematically invisible to one another.
Invisible?
Yes. Think about a force pushing straight down from the ceiling. It has absolutely zero parallel projection onto a force moving perfectly horizontally across the floor.
Because it's pointing straight down, it casts no shadow on the floor vector.
Exactly. They cast no shadow on each other. Despite crossing paths at that exact point, they operate with complete and total independence.
Thinking about two powerful intersecting forces being completely invisible to each other is genuinely mind-bending.
It changes how you see the world.
It really does. But the dot product only gives us a scalar result, right? It just spits out a single number telling us the degree of alignment.
Right, just a magnitude.
The notes then introduce the cross product, or vector product, which serves a fundamentally different purpose. If the dot product is about vectors sharing a path, The cross product is about vectors colliding to generate an entirely new dimension in 3D space.
And the formula shifts quite dramatically to achieve this.
Yeah, it looks totally different.
The text defines the cross product as the magnitude of vector A times the magnitude of vector B times the sine of theta, multiplied by a crucial new element called n hat.
Right, n hat. The text notes that n hat is a unit vector that is perfectly perpendicular to the plane containing our first two vectors, and it's dictated by what they call the right-hand rule.
Breaking out of two dimensions here is where the math truly comes alive.
It's where it pops out at you.
Literally.
Yeah.
Take two vectors, A and B, and just imagine them lying flat on your kitchen table. Those two vectors form a completely flat plane.
Okay, got it.
But the cross product does not stay on the table. When those two flat vectors interact, they generate a completely new third vector, that n hat, which shoots straight up off the table.
Perfectly perpendicular to both of the original vectors.
Exactly.
Now, the right-hand rule is this physical trick the notes give to figure out if that new vector shoots up toward the ceiling or down toward the floor, right?
Yes.
You point the fingers of your right hand in the direction of the first vector, you curl them toward the second vector, and your thumb points in the direction of this new third vector.
It's a handy visual aid.
I have to admit, though, I struggled with this initially. How does the math actually know which way this new vector points? Does this right-hand rule actually dictate physical reality, or is it just a clever trick we invented to visualize a purely abstract concept?
That is the big question. And the answer is the universe intrinsically behaves this way, which is a profound realization.
Wait, really? The universe just acts like that?
Yes. Electromagnetism, fluid dynamics, rotational mechanics, they all inherently follow this exact orthogonal three-dimensional relationship. The math and our little right-hand trick to visualize it is merely our human translation of an absolute physical truth. It is simply how the fabric of reality is wired.
That is amazing. And the text highlights another fascinating analytical property of the cross product as well.
Now, this is one of my favorite parts.
The magnitude of this newly generated vector, so its physical length, actually represents the exact geometric area of the spatial parallelogram formed by the first two vectors.
I will fully admit to getting overly excited about spatial parallelograms, but the elegance here is just undeniable.
It's pretty satisfying.
Imagine those two original arrows lying on your kitchen table. If you duplicate them and connect their tips to form a slanted box, a parallelogram, the flat area inside that 2D box is perfectly mathematically equivalent to the length of the new 3D vector shooting straight up out of it.
The 2D geometry and the 3D algebra lock together without a single wasted decimal point.
They perfectly mirror each other.
So we have built this comprehensive mathematical toolkit now. We have vector scaling to stretch and reverse forces. We have the dot product to measure how much forces align.
Right.
And we have the cross product to generate entirely new perpendicular dimensions.
So now we can actually build something.
Exactly. Stepping out of the theoretical textbook, let's look at the real-world engineering applications detailed in the source. Because this is where these formulas transition from just being study notes to literally being matters of life and death.
Particularly in aerospace engineering.
Yes, airplane.
Designing an aircraft is essentially a masterclass in vector manipulation. When engineers design control surfaces, like the ailerons on the wings or the elevators on the tail, they're constantly calculating aerodynamic torque and moment vectors.
And to calculate that torque, which is represented by the Greek letter tau, engineers use the exact cross-product equation we just unpacked.
Yes, they do.
Torque equals the radial distance vector crossed with the applied aerodynamic force vector. The interaction of those two things generates a perpendicular axis of rotation.
Consider the physical mechanism of an aileron for a second. It is just a movable flap on the trailing edge of an airplane wing.
Right.
When the pilot adjusts it, the flap moves into the rushing wind and the wind pushes back hard on it. That push is your applied aerodynamic force vector.
Okay, that makes sense.
But the aileron is attached to the wing at a very specific distance from the center mass of the airplane. And that exact distance is your radial distance vector.
Here's where it gets really interesting.
Right.
Because you can visualize this airplane cross product by comparing the aileron to a heavy, solid wood door in your house.
Oh, that's a great way to picture it.
When you want to open that door, you have to push on it. Your physical push is the applied force vector. The distance between your hand and the hinges of the door is the radial distance vector.
Right, and those two vectors work together on a flat plane.
But the result of those two things interacting, the cross product, is the swinging motion of the door itself.
The swing rotates around the hinges,
Mm.
creating a completely perpendicular axis of rotation.
And so the airplane physically rolls or pitches based on that exact cross-product hinge effect generated on its wings in the air.
It's the same math as opening a door, just at 300 miles an hour. But aerospace engineers do not rely solely on cross products.
Right, they need both tools.
The text points out that dot products are equally critical, specifically for calculating what they call wind relative velocity.
Resolving the aircraft's internal thrust, lift, and drag vectors against complex dynamic wind currents in the atmosphere.
Picture a commercial airliner fighting its way through a severe storm system.
A bumpy ride.
Very bumpy. The plane has its own thrust vector driving it straight forward. Simultaneously, the storm is hitting the plane with multiple wind velocity vectors from all these various random angles.
Right, coming from everywhere.
Engineers rely heavily on dot products to calculate the effective forward velocity component here.
So by measuring the parallel projection, that shadow effect we explored earlier on the highway, of the wind's force directly onto the plane's flight path, they can calculate precisely how much the wind is either assisting or degrading the aircraft's forward momentum.
Exactly. Navigating a massive machine through the sky fundamentally boils down to just measuring the shadows of vectors and calculating rotational hinges.
Which is incredible. And having explored those massive macro applications, the source notes shift scale completely. We shrink the math down to the subatomic level, and then we pull it entirely into digital software.
Proving just how universal these operations are across electronics and computing.
Yeah, the electronics section of the notes introduces the Lorentz force.
Right. This phenomenon occurs in particle accelerators and, funny enough, even in older cathode ray tube televisions.
Oh, those big, bulky TVs from the 90s.
Exactly. When a charged particle moves through a magnetic field, the physical magnetic force exerted on that little particle is determined by a cross product.
The text provides the formula for this. Force equals the electrical charge, multiplied by the cross product of the particle's velocity vector and the magnetic field vector.
This is a perfect example of why the cross product's geometric mechanism is so crucial.
How so?
If a charged particle is flying straight forward and a magnetic field is pointing straight up, the cross product dictates that the resulting force pushes it perfectly sideways.
Oh, because of the right-hand rule?
Exactly. It forces the particle entirely out of its two-dimensional plane, causing it to curve into a completely new dimension.
It is the right-hand rule governing subatomic reality.
The rules don't change just because things get small.
Right. And the notes also apply the dot product to electrical engineering, specifically in calculating AC power.
Yes. They detail that real power in an alternating current circuit can be modeled similarly to a dot product of the voltage and current phasors.
Now, to understand phasors, we have to recognize that AC power does not flow in a constant, flat line, right? Like water through a pipe.
Right. It operates in fluctuating waves. It goes up and down.
And phasors are essentially rotating vectors that track the peaks and valleys of those electrical waves over time.
And frequently, the voltage wave and the current wave do not perfectly synchronize. They are slightly out of phase.
So by treating these electrical waves as vectors, engineers capture the cosine of the phase angle difference.
Exactly. Just like the dot product measures the parallel shadow of two forces on a physical path, this calculates how much the voltage and current are actually aligning in time to deliver real, usable power to your household appliances.
It measures the mathematical alignment of electricity itself. That's so poetic.
It really is.
And the text proves these concepts aren't limited to just physical hardware. It moves into computing and graphics, outlining the mechanics behind the 3D rendering engines running modern video games and computer-animated films.
Rendering a photorealistic 3D scene requires calculating something called diffuse lighting.
Right.
The software has to constantly determine exactly how much light from a virtual sun or, a digital lamp is hitting every single pixel of a 3D surface.
Millions of pixels.
Millions of them, 60 times a second.
And the rendering engine computes this by finding the dot product between the surface's normal vector, which the notes describe as an invisible arrow pointing straight out from the 3D object, and the light source vector.
Right.
The text states that a dot product of 1 indicates the light is hitting the surface perfectly directly, resulting in maximum brightness.
Pure daylight.
Yeah. But a dot product of 0 or less means the surface is entirely in shadow.
Because if the incoming light vector is perfectly perpendicular to that surface normal, the angle between them is exactly 90 degrees.
And the cosine of 90 is 0.
Exactly. The light rays are simply skimming past the surface without transferring any illumination whatsoever.
It's all just math. Video game engines heavily utilize cross products too, especially for physics and collision detection.
Oh, definitely.
When your virtual character throws a digital object against a complex wall, the engine uses cross products to dynamically generate those surface normals for the 3D meshes.
Those thousands of tiny mathematical triangles that make up the shape of the wall.
Right, generating those perpendicular vectors allows the software to calculate the exact angle of the physical bounds.
If we connect this to the bigger picture, a really gorgeous symmetry emerges in how these two equations govern both physical and digital reality.
Oh, absolutely.
Dot products beautifully govern alignment. They measure shared pathways, whether that's calculating the phase angles and alternating electrical currents, or determining how perfectly light rays illuminate a digital surface.
And cross products govern spatial physics and collisions.
Right. They generate the perpendicular forces that dictate how a subatomic particle curves in a magnetic accelerator, or how a digital object realistically bounces off a wall in a physics engine.
That is an immense amount of structural responsibility placed on just a few lines of math.
It's the heavy lifting of the universe.
Yeah. But now that the sheer scale of these real-world implications is clear, we have to ask a practical question here. How do modern engineers actually execute this work?
Oh, right. Because doing it by hand would be a nightmare.
Exactly. The math is elegant, but manually calculating the spatial area of millions of microscopic digital triangles or constantly resolving changing wind vectors on a flying aircraft, it would be utterly impossible to do by hand.
It would bring modern engineering to an absolute standstill.
So the final section of the source text addresses this directly by providing what they call a computational proof.
It highlights a standalone script designed to execute these precise vector operations programmatically.
The notes explain the script is built to run immediately in a standard Jupyter Notebook cell.
And for those unfamiliar with that, a Jupyter Notebook is a highly interactive digital environment. It's widely used by data scientists and software engineers to basically combine live code, equations, and narrative text all in one place.
It's a really neat tool, and the script utilizes two specific software commands, numpy ... and numpy.cross.
NumPy is a fundamental programming library in Python. It's specifically designed for high-level mathematical functions like this. So by invoking numpy ... and numpy.cross, a computer can instantly verify orthogonality and compute the geometric area of a spatial parallelogram across thousands of vectors simultaneously.
Taking these abstract trigonometric formulas we've been talking about and turning them into singular lines of code, it fundamentally shifts the scale of what humanity can build.
It completely changes the entire paradigm. What used to take pages upon pages of manual arithmetic can now be executed in milliseconds by these software libraries.
Freeze them up.
Exactly. By automating the calculations, tools like NumPy free modern engineers to focus entirely on the applications. They get to dedicate their mental bandwidth to manipulating the physics of the aircraft or dialing in the lighting in the software engine, rather than worrying if they missed a negative sign in their cosine calculation.
Which is so easy to do.
Oh, I've done it a million times.
Right. Well, as we wrap up this deep dive into the source material, let's just reflect on the incredible journey embedded in a single day of high school study notes.
From a classroom in India to the edge of modern engineering.
Exactly. We started by mapping abstract arrows in space, learning how to stretch their magnitude with a volume knob and reverse their direction completely.
We utilized the dot product to calculate parallel projections and shadows on a highway.
And we explored how the cross product leverages the right-hand rule to force entirely new perpendicular dimensions into existence, like pushing open a heavy oak door.
It's a lot of tools in the toolbox.
It really is. The ultimate takeaway for you, listening, is that this mathematics is far more than a classroom exercise.
It's not just theory.
No. Whether you are boarding a commercial airliner, trusting the aerodynamic torque on the wings, or plugging in a household appliance relying on electrical phase angle alignment, or even just navigating a 3D video game world completely dependent on collision meshes, you are directly interacting with dot and cross products.
They are the invisible logical framework keeping the modern world in motion.
Beautifully said.
This raises an important question, though. A final way to view the relationship between pure mathematics and human perception.
Oh, I love where this is going.
Let's draw a final parallel between the raw equations and the digital reality we explored earlier. In 3D graphics, as we discussed, a dot product of 0 or less means a surface is completely unlit entirely in shadow.
Right, because the light skips right past it.
Exactly. But in pure structural mathematics, a dot product of zeros signifies perfect orthogonality. It means two vectors are completely failing to align or cast a shadow on each other in any way.
The mathematical forces simply cease to interact on the same path.
Right, so it leaves you pondering. The next time you are playing a video game and your digital character steps out of the bright sunlight and into a dark corridor, realize you aren't just looking at the absence of simulated light.
No.
No, you are staring directly at a mathematical state where two geometric vectors have simply ceased to agree.
The darkness is quite literally a lack of mathematical alignment. That is incredible. Well, thank you so much for joining us at the table today to unpack the hidden logic of the world. Until next time, keep exploring.